Alright, hi guys. The topic of today's video is reaction rates, specifically chemical reaction rates. Do they take time? Do they happen instantaneously? If they do take time, why? Why is that the case? Can you speed up a chemical reaction or can you slow it down? What affects the speed of a chemical reaction? That's what our topic today is all about. The very first thing we kind of want to mention, or we want to pose this question: why do chemical reactions happen at all? So let's write that down. Why do chemical reactions happen in the first place? So why do they happen? First and foremost, we can say that, well, actually, let's write an equation. I think that'll work out much better. Let's write an equation between water, H2O, and what? What sounds like a good reaction to have? Water and phosphoric acid, H3PO4. So I'm not going to write this reaction in equilibrium. I'm just going to write it as though it's going to the right only. When phosphoric acid and water combine together, so that addition symbol means that they combine together, what happens? Well, that phosphoric acid is going to lose one of its protons. It's going to lose a proton to form H3O+, and that H3PO4 is going to be turned into H2PO4-. Okay, so why did that reaction happen? There really are a number of reasons. I mean, it goes all the way from electronegativity to concentration, pressure, and temperature, all affecting why it happens. What we can say is that at the very simplistic level, the reaction happens because the H2O molecule and the H3PO4 molecule get close enough with enough force and enough energy to react. Before we kind of write that down, and we will write it down, let's write that, just in case we forgot, the stuff on the left side of the equation, which is, separated by the arrow, are the reactants. Okay, the stuff on the right side of the equation are the products. That is super important. If you do not know that now, or if you didn't know that before now, hopefully you do now. Kind of leave that up there for a second so you can take a look. All right. So why do chemical reactions happen in the first place? Well, we do need to say a nice, short, abbreviated something about why they happen. So we said before that they happen because the reactants, all the molecules in the reactants, usually, combine with enough force and enough energy to make a reaction happen, to exchange and rearrange atoms. So let's write that sentence here. Chemical reactions happen because all the molecules, all the reactants, I should say, collide with enough force. Oh, let me get my hand out of there. With enough force / energy to make the chemical reaction happen. To make that word is the, my E looks terrible on it, I apologize. To make the chemical reaction happen. Okay, so that is an incredibly important statement. We could talk all day about that one little sentence. All day indeed. If we want to think even just hypothetically about what can change the speed of a chemical reaction, we can focus in on the force and energy part of that sentence. So let's read the sentence one more time. Chemical reactions, whoa, I should have read that in the first place. Chemical reactions happen because, holy cow guys, it wouldn't be me without some sort of awful spelling mistake. Okay, well, chemical reactions happen because all the reactants collide with enough force and energy to make the chemical reaction happen. Not all chemical reactions require tons and tons of force. Some require just a little teeny tiny bit. So we are going to look at a chemical reaction that takes very, very, very little energy. It is the reaction of hydrogen gas and oxygen gas. Not at equilibrium, just one arrow to the right. They're going to combine together to make water. Take a second to balance that equation. I don't think it should take you very long. Do 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 do. Okay, so there we go. There's the balanced equation. Why does this reaction take almost no energy to happen? It just takes a little spark for the hydrogen gas to react with the oxygen, and you get a huge boom and a bunch of water is produced. So why doesn't it really take a lot of energy for this to happen? Well, we can say that these are high energy molecules. This is a low energy molecule. When high energy molecules collide, they release a lot of energy to form a low energy molecule. So what does this really, really mean? We're going to draw what's called a reaction progress diagram to explain that. So this is a reaction progress diagram. All right, our diagram is going to look like a graph. Don't freak out. Graphs are your friend. Okay, so there's our graph. On the y-axis, we're going to have energy. So write that on your y-axis. On the x-axis, we're going to have reaction progress. Reaction progress. I apologize, my writing gets really sloppy at the bottom. Don't know why, kind of weird. All right, so this is reaction progress on the x-axis. All right, so we're going to say that our reaction is going to start by taking some amount of energy, or there's some amount of energy present in the molecules. So if we say this is zero energy and zero reaction progress, our reactants, the stuff over here, stuff on the left side, oops, this stuff over here, there, now you guys can see that, start with some energy. Okay, so let's start with some energy, and then all of a sudden something weird happens. It takes some energy for the reaction to start, and then the reaction finishes. The reaction finishes, the products of a reaction usually have less energy than the reactants. So here we have reactants, 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 nothing's happening, oh, something's happening, we don't know what. And then the reaction kind of comes to a close. And then we get the products over here. The products have less energy than the reactants. This giant hump in the middle is what we call the activation energy, or E with a little subscript A. It's the activation energy. It's how much energy it took to start the reaction. So I'm not sure if this is very accurate for hydrogen gas and oxygen gas, but hey, it's just a rough estimate here. So let's kind of put this into words. It takes the hydrogen and the oxygen have some energy. Who knows how much? We could look it up if we wanted to, but this is just, kind of a conceptual thing. They have some energy when the reaction starts. Before the reaction starts, I apologize. They have some energy here. Then someone put some energy in. Maybe it was a spark, maybe it was a flame, maybe it was just some random spark of fire. Who knows? Someone put some energy into the reaction, and then the reaction started happening. Okay, and the reaction's kind of coming to an end here. When the reaction finishes, this lower line is going to be our products. Make sure your dotted line is filled in correctly, just like mine. That's the activation energy. Let's go ahead and label that now so we have it. So the activation energy. It's the minimum amount of energy. The minimum amount of energy required. Let me make sure I don't get too ahead of myself here. to start a chemical reaction. I think I need to get a new Sharpie. So the key word is minimum amount of energy required to start a chemical reaction. There are molecules that lower the amount of energy required to start a chemical reaction, and that's what we're going to talk about in just a second. Fold a new piece of paper. You guys should have had enough time to write that down. If not, you can pause, or I can pause if this is done in class. Okay. Oh, there's someone at my door. Okay, so right after, at the new video, we're going to talk about catalysts.